Let's let's continue with this. Okay, again, we were trying to find the average rate of change on this particular function, okay, on the interval from 0 to 3. And the application of this says that the average rate of change would actually be, okay, the average velocity. And so we're going to resume with this now, okay? And we're going to ask to find the average rate of change on the interval a to b for the function x squared. So the ARC, the average rate of change, the ARC, is equal to the slope, which is the difference in the y over the differences in the x. Remember, the y's are simply the function evaluated at a and the function evaluated at b. Okay? Now, what is our function? Our function is x squared. F of b is simply plugging in b as a new x and squaring it, which really can't do anything more than just say, oh, it's b squared. Okay. Likewise, f of a, okay, is again plugging in a here, which would just give us a squared. Okay. Now, so we have b squared minus a squared over b minus a. Well, we should actually naturally see that that this will factor as a difference of squares, b minus a over b plus a. And the b minus a's will cancel out between the top and the bottom, resulting in the b plus a. So, generally speaking, the average rate of change from a to b on the interval a to b for the function x squared is b plus a. Now, you might recall that we did this. I'm going to go back a little bit. Just bear with me. We did this, okay, average rate of change on a particular interval, 2 to 4. And that proved to be the average rate of change is 6. So let's move ahead now back to where we were, okay. So previously, as we saw, the average rate of change on a particular interval, 2 to 4, was 6, which is, this is the, from A to B, A being 2, B being 4, simply says, let's just plug those back in. And then, of course, this gives you 6, which is in agreement with what we found earlier. So effectively, this generalized approach for this particular problem in computing the average rate of change will work for us regardless of the interval. So let's see if we can take a smaller interval. Okay, so if the interval is kept very small, then the average rate of change becomes a very good approximation for the instantaneous rate of change. Okay, so that'll be a very important concept when you start talking next year in calculus about rates of change. It'll be a very important concept. So if I said, what is the average rate of change on the function x squared on the interval 2 to 2.01, or on the interval 2 to 2.001, then simply go back to the generalized formula, and it's simply a plus b, which you can do quite easily. So the first one would result in 4.01, and the second one would result again just by formula adding the a and the b values up here, 4.001. So the calculus would actually show us that the instantaneous rate of change, which would be the slope of the line between 2 points so close that the 2 points are actually 1, and that would actually show that that's moving towards 4. So this is a step in that direction. But again, the main concern here is computing the average rate of change on this general interval, and then maybe later tailoring it to particular intervals as noted here. Let's do that again with another example, okay? So let's take that previous example with the object being thrown up, and this being the velocity equation as a function of time. Let's do that, generally speaking, finding the average rate of change between A and B for this particular function. So again, by definition, our average rate of change is as stated here. Okay, f of b minus f of a, f of b minus a. And in this instance, it means going back and just replacing the t value with a b, okay, and then replacing with an a and taking their difference. So let's take a look. Okay, f of b, negative 16b squared plus 128b minus, okay, f of a, which is negative 16a squared plus 128a. Now, with here, what we really want to do is we want to be able to combine some terms up here in the numerator so that we'll get a cancellation with the b minus a in the denominator. So we'll proceed on that front, okay? First thing I did was, again, since this was a difference, everything in the parenthesis, which is in fact the f of a, is going to be impacted by that negative sign. So, so that these signs are altered. Now, there is a common factor, I believe, that of negative 16 that can be pulled out, and that's pulled out. Now, the remaining expression can be factored by grouping, okay? So we should be able to see a b minus a, b plus a over here, but we also should be able to see over here that 8 is common to these two factors. So let's proceed to factor that accordingly. So here are the difference of squares factors as shown, okay? And then 8, negative 8 comes out, making this b minus a. Now, the numerator contains a common binomial factor in the form of b minus a, okay? B minus a, which comes out as a common binomial factor, as shown down here, okay? So, so now the numerator is fully factored, okay? B minus a is common to b plus a minus 8. We get a nice cancellation of the b minus a expression, okay, leaving us with this as our final expression. So this is the average rate of change on the interval a to b for this function f of t equaling negative 16t squared plus 128t, okay? That is the expression. Go through. You have to be very careful every step along the way. Write down the general form, okay? Evaluate the function with b, with a. The difference, I intentionally wrap the whole f of a term in brackets because I don't want to ignore the impact of that sign preceding it, okay? And then you have to factor with the intent that somewhere you have to find a common factor of b minus a in the numerator, which will facilitate a nice clean simplification, the canceling in the numerator and denominator, okay? Previously, we looked at the example of this, and maybe I'll just run back to that for a moment, okay? Previously, we computed that average rate of change on that specific interval, okay? Referring back to this problem, compute the average rate of change on this specific interval from 0 to 3 for this function, which we found it to be 80. Now, returning to that to illustrate now, okay, the formula, negative 16b plus a minus 8, okay, b being 3, a being 0, okay, basically says, okay, place those values in for b and a respectively in this very generalized ARC. And of course we get 3 plus 0 minus 8 is negative 5 times negative 16, which is 80, which is consistent with what we found previously. Okay? And if we wanted to do that on a smaller interval, uh, we would be moving our average rate of change closer to the instantaneous rate of change. And so if we took the interval very small, from 2 to 2.01, that is, find the average rate of change over 100th of a second. Okay, that's what this interval is. It's just a difference of 100th of a second. Then we can use this formula, okay, with the b value of 2.01, okay, and the a value of 2. So we plug those in to our formula down here, and we come to a value which is very close to 64 feet per second, which would be in physics as well as in calculus, would prove to be the instantaneous rate of change. And this is moving you towards an understanding of how in that course next year you'll be able to compute those things in a process called the limit. Okay, but for now, all we need to know is to be able to run through this series of computations, okay, and get a generalized formula for the ARC, and then if asked, okay, we can tailor it to a specific interval, okay, regardless of how small. And in fact, the smaller the interval, the closer the approximation to the instantaneous rate of change that we're finding, okay, as opposed to the average rate of change. So that's it for this presentation.